Page 9, example 2.2. This is an example of a time sequence in which the process is covariant stationary, and you can just follow along with what is shown on page 9 on the top half of the page. So we're looking at a process for which zt is equal to a times the sine of omega t plus theta, where a is a random variable with the mean of a equal to 0 and a having unit variance. There's also a random variable called theta, which has a uniform distribution on the interval from negative pi to positive pi, and theta is independent of a. So the two random variables a and theta are independent of each other. The rest of them constant. Let's compute the mean, the expected value of zt. Now I want you to rewrite equation 2.1.9 a little bit. Right now it's zt equals a times the sine of the sum of omega t plus theta. I want you to write let x equal a, let y equal sine of the sum of omega t plus theta. So you're going to rewrite that equation as zt equals x times y, where a is a random variable and a is the same as x, so x is a random variable and they're independent of theta, so they're independent of the sine of the sum of omega t plus theta. I also want you to go to Wikipedia, the website. Under contents you'll see that the third section is properties, and within the properties section there's a subsection called non-multiplicativity, and you see an equation there where it says covariance of x comma y is equal to the expectation of the product xy minus e of x times e of y. So if you know that covariance is positive, then you know that the expectation of xy is greater than e of x times e of y. Similarly, if you know that e of xy is greater than e of x times e of y, then you know that covariance is positive. And you can see the reason why e of xy would be greater than e of x times e of y. Let's say e of x and e of y are both equal to 0, so if they were independent, the product would just be 0. E of x times e of y would just be 0. But let's say that they're positively correlated, in which case you have positive values of x associated with positive values of y and negative values of x associated with negative values of y. So the product xy becomes positive in both of those cases. It's less likely to have a negative value of x or a positive value of y, or a positive value of x, negative value of y. So you end up with an expectation of xy that's positive, which is greater than 0, of course, which is the expectation of x times the expectation of y. Covariance can also be negative, of course, if variables x and y move in opposite directions. And in that case, the expectation of xy would be smaller than e of x times e of y. The reason for this, again, being apparent in an example where expectation of x is 0 and expectation of y is 0, now you have negative correlation or negative covariance between x and y, so positive values of x associated with negative values of y, negative values of x associated with positive values of y. Product of those is a negative number in either case, and that's more likely than having negative x and negative y together, or positive x, positive y together, with the product being positive. So expectation of xy becomes less than 0. Now, if covariance is 0, that means the variables x and y do not move in relation to each other at all. They're independent of each other. Then the expectation of xy is equal to e of x times e of y. And you can see why Wikipedia refers to covariance as the extent to which multiplicativity fails. I think that's an interesting way to describe covariance, and you could think correlation the same way. Getting back to our rewritten equation of 2.1.9, where we have zt equals xy, we can take expectations of both sides. So that means on the left side we have e of zt, and on the right side we have e of xy. And because these variables are independent, x and y, then we know that e of xy is equal to e of x times e of y. So you see in the next line it says e of zt equals e of a times e of the sine of the sum of omega t plus theta. Now we know that the mean of a is 0, and so we know right off the bat that the expectation of a is 0. 0 times the rest of it, e of the sine of the sum of omega t plus theta, that's all going to be equal to 0, because you just have 0 times something, and 0 times anything is 0. So the expectation of zt is 0. The mean zt equals 0. Let's look at zt plus k. We now know what the expectation of zt looks like. the expectation of zt plus k looks the same, except the t is replaced by t plus k. To get the expectation of zt plus k, can I just multiply expectation of zt times expectation of zt plus k? A multiplied by a is a squared. Since we know that theta is independent of a, the terms within the expectation that involve a and the terms within the expectation that involve theta, those can be factored apart from each other. So you have expectation of terms involving a times expectation of terms involving theta. This is just like our rule that if expectation of xy has x and y independent, then expectation of xy is equal to expectation of x times expectation of y. So that's how we get to the second line of our derivation of equation 2.1.10 on page 9. Note that Dr. Wei also has done some changes with sines and cosines in there. I'm not going to explain how that works. If you don't know, you can reference that yourself. It's not going to be critical to the course to know this trigonometric stuff, so I'm not going to spend time on it. Now that you see expectation of a squared, bells and whistles should be going off in your mind, and you better hope that the expectation of a is equal to 0. Why? Because there's a rule that if you have expectation of x squared and the expectation of x equals 0, then the expectation of x squared is equal to the variance of x, because variance of x equals expectation of x squared minus expectation of x quantity squared. And if expectation of x is 0, then expectation of x quantity squared is also 0. So variance of x equals expectation of x squared. So expectation of a squared is equal to variance of a. We know that a has unit variance, which means variance of a is equal to 1. So that just disappears. 1 times something is just something. Now, since theta is a uniform random variable, and we must calculate an expected value using the interval from negative pi to positive pi, theta's uniform distribution means that the probability density from negative pi to positive pi will be 1 over 2 pi. Now, I'm not going to get into the details of trigonometric integrals. Suffice it to say that you'd end up with equation 2.1.10, in which all that's remaining is 1/2 of cosine omega k. So your covariance does not depend on t anymore. Covariance only depends on the time difference k. So our process is covariance stationary by our definition, in that a process only depends on the time difference k in order to be covariance stationary, aka second order weakly stationary. So this is a covariance stationary process.